Now that we've talked about analytic functions, let's get into holomorphic functions. So holomorphic functions are going to be functions that have some notion of a complex derivative. So we have a function f on a domain omega. We say it's holomorphic if this difference quotient, using complex numbers now, so it looks like the standard calculus difference quotient, but we're taking a limit in the complex plane as z goes to z naught, and we're asking for this, change in outputs over change in inputs to tend to something, and this has to happen for every z naught in the domain. And when this limit above exists, we can call it the complex derivative, and we use this notation f prime of z naught for this. So it all looks very much like calculus, but it turns out it's very different from standard calculus on the line, because this property for the complex numbers is much stronger. But before we can see that, it's useful to point out some things that hold just like for calculus. So if I have two holomorphic functions, we have all of these nice kind of closure properties that maybe these would be a little tedious to check for analytic functions, but for holomorphic functions, these are pretty, the proofs are just like from calculus. So a sum of holomorphic functions is holomorphic, product. The quotient is holomorphic whenever at points where the bottom is non-zero, and then we have the usual derivative formulas for complex derivatives as we do for standard derivatives from calculus. And these kinds of proofs that a derivative exists behave much like they do in calculus. So to show that z to the n is holomorphic, well, I mean, I could just prove that z is holomorphic, which is trivial, and then use like the product rule to show that z to the n is holomorphic. But you could sit down and attempt to do it with a difference quotient, and then you just need to do a little bit of algebra just using a formula like this. And this is the summation version of that formula. And you'd send z to z naught and get the usual formula you expect, that the derivative of z to the n at z naught is n z naught to the n minus 1. It was wrong there. And so we have this formula here. And then you get that polynomials are holomorphic, rational functions are holomorphic, away from the zeros of the denominator. So what is a function that is not holomorphic? Well, functions that look nice sometimes are not holomorphic. And the intuition here is that functions depending on z and combinations of z's are going to be holomorphic, but things that depend on z bars, in any meaningful way, these things will not be holomorphic. And you can just sit down and prove that z conjugate, f of z maps to z conjugate is not holomorphic. You write out the difference quotient, and if I write the top, or if I write z minus z naught in polar coordinates, then the top, so the bottom will be r e to the I theta, and then the top will be the conjugate, so the r's will cancel, and you just get this e to the minus I2 theta function here, which as r goes to 0, which is equivalent to z naught going to z, this tends to different things kind of depending on which direction you're going. So it doesn't tend to a consistent limit, and that's why z bar is not holomorphic. Okay, so here's one of the most important functions in complex analysis, the exponential function, which initially we can define with a power series. And And you can show that this converges for all z. And then, it's not, again, we haven't proven this, that having a power series representation implies that it has power series representations at other points, but it will be true based off of theorems we present later. But it turns out you can use this to show that e to the z is analytic everywhere. It satisfies the usual rule that we're used to for real values, so e to the z plus w equals e to the z times e to the w. Its complex derivative is itself. We can break it apart using the real and imaginary parts of z into e to the x times e to the iy, and it breaks apart into, well, e to the iy does equal cosine y plus I sine y for y real here. And what else can we say? The modulus of e to the z is just going to be e to the x, and that's because e to the iy has modulus 1, and that's just because if we compute the modulus squared here, you're computing cosine squared plus sine squared. And again, we're not following some kind of consistent path through these proofs, so this is just to kind of give you a feel for the situation. Okay, what else can we say? Well, it's good to know the points where e to the z equals 1. How would we solve for that? Well, we'd have e to the x, e to the iy equals 1. Well, for the modulus of this to be 1, e to the x has to be 1. And the only way that can be true is if x is 0. And then we have to figure out when is e to the iy equal to 1. And then we look at the trig functions here, and we see that it's only when y is a multiple of 2 pi. And so that's equivalent to saying that z is a multiple of 2 pi I. So these are exactly the solutions of e to the z equals 1. And I think I already said this here, but the modulus of e to the z will just be e to the x. So this is 1 only when the real part of z is 0, i.e. x is 0. And we can answer other questions here. So like, for which z is e to the z equal to 2, and we could go through kind of the same procedure. When do I have this? Well, the modulus of e to the z is e to the x, so then we would still have e to the x equals 2, so x would have to be natural log of 2. That's the only solution to this for real x's. But then, so once we have that established, then we're back to our usual, the formula we just established up here. And then the possibilities for y are the same as before. So the solutions to this are not just natural log of 2, that works, but natural log of 2 plus 2 pi I times integers. All right, now we're going to make a long story short and just tell you the following fundamental fact, which is being analytic is the same as being holomorphic. And proving this takes up quite a bit of time in a complex analysis course, and just kind of assuming it saves us a ton of time. So we can, if you believe this, we can move on to some really interesting things. The easy part of this is showing that analytic implies holomorphic, because if I have a power series representation centered at some point z0, then it's not too hard to just dig into the infinite series and show that I can take the derivative term by term as long as I'm staying in a disk of convergence for the original power series. The hard part here is showing that holomorphic, which is just this like highly localized, simple property of a complex derivative, that implies that you have this full power series representation. And again, you have to build a lot of tools to prove this, and it takes a bit of time, and so we're just going to accept it. And so what is the point of this? Well, being analytic gives you many nice local properties. So for instance, if f is analytic and it has a 0, then I can show that I can divide out the 0 essentially. F over z minus z naught will be analytic. And the reason is f will have a power series representation, but the first term is missing because it equals 0. And then that means I can factor out a z minus z naught part. And then the remaining part is still this nice convergent power series, and it will be analytic. And now I can just divide, and so f over z minus z naught is analytic. And you could do this as many times until you got to the first non-zero term. So I could always do something like, at any point where I have a 0, I could divide out a certain multiplicity of zeros to get a function g that's analytic at z naught, and I've wiped out the 0. You could do this as long as f is not identically 0. Okay, and what else? So here's where we get into Taylor's formula for the coefficients. So I already said that f being analytic means it has all these complex derivatives, and so how do they relate to the coefficients? Well, the value at z naught gives me the first coefficient, and then if I take the derivative like I did above, I get this formula here, and so its value at z naught is going to give me c1. And then you keep applying this formula over and over, and you'll get a general formula for the nth coefficient is the nth derivative at z naught divided by n factorial. Okay, but not only can we take derivatives, we can take local antiderivatives. And it's not so obvious how you do this with holomorphic functions, just working with that definition, but once we have a local power series representation, I can just go through and take antiderivatives term by term. You would have to verify that the thing here still converges, but it does, and we'll talk about different convergence things soon, but I can just get a local antiderivative. Again, so let me just summarize that the point of this is holomorphic is kind of an easier condition to check. It's easier to establish various closure properties, but once we know that's equivalent to analytic, then holomorphic functions will have all of the same properties as analytic functions, and all of these nice local behaviors of power series then will be properties of holomorphic functions. Now we need to talk about a slight generalization of analytic functions that will come up all the time for us, and these are called meromorphic functions. And the quickest way to define meromorphic functions is to define them kind of as quotients of analytic functions. So a function h, just defined on here, this is a punctured disk. So the disk centered at z naught with z naught removed. It's meromorphic if it has a representation as f over g, where f and g are analytic on this disk, and g here is non-zero away from z naught. And so when we do this, what exactly happens? Well, we can factor out zeros and see that h has a very particular form. So as we said over there, right here that f, we can factor out all of its zeros so that I get a piece left that does not vanish at z naught, and I can do the same thing with g and get a g naught that's non-vanishing at 0. And now h, when I divide these two, it'll just have this factor of z minus z naught to some power. So n minus m, could be positive, could be negative, could be 0, all are possible. This part here will be analytic on the disk in question because g naught now will have no zeros. And what can we do? Well, I can take this analytic part and it will have a power series representation. And then if I expand the power series here and then just multiply through by this potentially negative power, what I get is not a power series representation, but it's what we call a Laurent series representation. So it's like a power series, but we allow some negative powers, only finitely many negative powers. And so this is maybe a better way to think of meromorphic functions. They locally have this generalized power series representation, so where we allow a finite number of negative powers in our series representation. And then I have a note over here. If this number k, which is m minus n, so that's the negative of the power here, if that's positive, meaning I have a negative power here, then we say that h has a pole of order k at z naught. And then otherwise, h is just analytic at z naught, and we're kind of back into the discussion we've had before. Okay, and now we can introduce this humble-looking definition that will be very important later on, that for a meromorphic function, we have a special name for the coefficient of this term in its series expansion. So up above, h here could, we could start out at minus k and have some coefficients with negative powers. And then we get to this term that's just to the -1 power. And then maybe we have some just regular power series terms. But we give a special name to this coefficient. It's called the residue of h at z naught. And it plays an important role in various theorems to come, the residue theorem. And it's important because it's kind of a compositional invariant in some sense. But for right now, you just have to kind of take it at face value that we call this coefficient the residue, and you'll see why it's important later. Okay, so to summarize most of what we've done so far, we've defined analytic functions, and these are these functions that locally have power series representations. We have holomorphic functions, which have complex derivatives. We've said that these two things are equal, and we've defined this slight modification of holomorphic functions where we allow some negative powers. Now with this overview done, we're going to get into some convergence properties of power series at last, because we're going to be interested in using complex analysis and ideas around holomorphic functions to estimate coefficients of power series.